I built a satellite tracker that uses magnetometers and accelerometers for position sensing for satellite tracking. But why is this important? First, we need to go back to the beginning of this project, and I'll let my younger self explain how it started.
So when I was 8 years old, I wanted to contact the ISS. So I asked my dad, how can I contact the ISS? And he said, well, I don't know. So we got online and we found this place called Eris, and they managed to get a ham radio up onto the ISS.
Shortly after asking that question, I acquired my ham radio license on the third try. I then built a helical antenna to contact the International Space Station, and I added a second winding for the 70 centimeter band, so that I could use it for the ISS repeater.
That's correct, CN85, KJ7LL.
I custom built the satellite tracker for this ISS repeater contact out of Legos, using a potentiometer for position sensing. But hold up, why is position sensing important? Position sensing is important because it tells you where your antenna is pointed. This allows you to point your antenna at a specific repeater or point it at a satellite as it passes overhead. Now, the reason to use a magnetometer instead of a potentiometer is because if you use a potentiometer, they have limited rotation and they will twist up. We'll get to how I built a satellite tracker using magnetometers and accelerometers in a minute. But first, let's continue with this story. A year later, Cadence Design Systems invited me to present at Cadence Live 2023, where I won Best in Track in Multiphysics and Design Analysis. Then I made my first ISS repeater contact, and I was invited to present my project at the Cadence booth at IMS. Finally, I was also invited to present at the Design Automation Conference. After all the conferences, I heard about the Northwest Science Expo, or the Oregon State Science Fair, but because I only heard about it in December, that meant that I only had 3 months to complete my project before judging. My project was to make a 3D printed desktop satellite tracker that used a magnetometer and accelerometer to get position sensing. Because of my desire to talk to an astronaut on the ISS, I got involved with ERIS, NASA's educational outreach program that schedules amateur radio calls with schools. When my project was judged at the science fair, it received first place in the engineering category and best of fair in middle school. Then, ERIS actually accepted the proposal, which meant that there would be a contact between Teach Northwest students and an astronaut. After the ERIS proposal was accepted, I gave a Tech Talk presentation at the Teardown 2024 Engineering Conference about my desktop satellite tracker. Then, ERIS gave the contact week of October 14th. From this date on, I was using 10-hour days to prepare, design, and build my full-size tracker for the ERIS contact. Remember how I got Best of Fair at the Science Fair? Well, that came with a nomination for the National Science Fair, and I was selected as a Thermo Fisher Scientific Junior Innovators Challenge finalist, and I got second place in the math category for my desktop satellite tracker. You may have noticed that there were 2 stories intertwined here, the science fair and the ERIS contact. I can use the same technology that I used for the desktop satellite tracker to help with the ERIS contact. Because the desktop satellite tracker used a magnetometer and accelerometer sensor for position sensing, that's what I'm going to use. So, let's continue with the ERIS story. To help with preparation, I led a 6-hour antenna building workshop to build the antennas that would be used to contact the astronauts on the ISS. To make sure that all the systems were working before the contact, I would go out to the location twice a week, set up, troubleshoot the problems, and tear it down until all the issues were fixed. Now, let's talk about the electronics used in the trackers. I used 3 GPIOs to control 5 buttons by using diodes. So the first button connects to GPIO 1, and the third button uses a diode to connect GPIO 1 and GPIO 2 to get binary 3, so that's how we know it's the third button, and the same for all the others. Now that's the ESP32, which is the brains that controls it all, and these are the contacts on the bottom of the board, which connect to the rings on the circle board so that it can rotate indefinitely. And here we can see the magnetometer and accelerometer there, and that's a little bit about the circuitry. Finally, after 5 weeks of testing and redesign, the ISS contact successfully occurred on October 18th at 11:30 a.m. Pacific Time. This was it. The culmination of the past 5 years had all led to this. facilitating a contact with astronaut Sunita Williams over amateur radio. Anyone SS? Anyone SS? Anyone SS? This is Kilo Juliet 7 November Lima Lima.
Kilo Juliet 7 November Lima Lima. This is November Alpha 1 SS. Over.
Media really likes this kind of event, and following the contact, there were several news articles. On October 30th, 2024, I met the director of the ERAS program, Frank Bauer. This is when I learned that I was the first person in the history of ERAS, since it started in 1996, to use completely homemade equipment in an ERAS ISS contact. I designed and built two main rotors, which I showed here, the desktop satellite tracker and the full-size tracker. To understand the differences, let's take a closer look at how they're built. So the first thing that we're going to do is put the circle board in, and then attach the baseboard. Then we will screw in the baseboard, and make sure that it doesn't fall out, and you can see how the circle board rotates. Now we put on a shield, and attach the upper body. You can see how the upper body slides onto there. This is the ring that holds the upper body on and holds it together while it's rotating in the azimuth direction. Then we install a bottom cover, which is not only a shield but also helps to hold the motor, the azimuth motor, onto the body. Then we connect a large gear to the accelerometer, which fits right into that slot there, and it rotates straight down like that. And that's how it rotates around when the worm gear turns. Now I attach a cover. This cover has been designed to have plastic that goes over the upper body to keep rainwater out. And then we screw it together, and you'll notice on these screws that they have little rubber flanges that open up so that rainwater does not get in through them because they're vertical. You'll notice here we have the magnetometer, which senses azimuth position. Now we move on to the desktop satellite tracker, and we'll start by assembling the elevation section. So we just put the motor in there and stick a pin through to hold it in place. And then we see the accelerometer is right there, and that's the magnetometer to sense azimuth position. And then that all goes into the tube. And then we have little bushings, which spin when elevation turns. Now we assemble the planetary gear system, and first things first, we put on the planetary gears, and you can notice how there's the blue gears are the planetary gears, the black are the carriers, and the white on the bottom stage is the triangle gear. And that spins when the lower carrier spins, and as you can see, when I turn the inner drive gear, it turns the whole planetary gear system. And as you can see there, the circle board places right onto the cutout in the motor triangle, which is where the motor sits. Now we attach the baseboard, and you can see on the cover, the cutouts are for the different parts on the baseboard. So we have the buttons, the LCD screen, and the GNSS, and those buttons push onto the buttons on the baseboard. Now we stick in the big phi gear, which rotates the elevation module, and the square shaft that goes through it and holds the antenna holder. And once that's through, we can attach the accelerometer into the antenna holder so that it rotates when elevation rotates. And then we add little spacers to hold it in place. And as you can see there, the motor just goes into the motor triangle. You can see how it fits into the FPC connector. And once the motor is in, we can attach the antenna. Now you can see how the technology is the same and the trackers are very similar. The only difference is really they're outside, because one is made for permanent installation outdoors and the other is for your desktop.